Welcome to the video Help with Physics Problems for Physics 1A. In this video we'll be covering homework set 6, part 1. This is everything under the heading Wave Motion. For 1121 students this is questions 1 to 5. For 1131 students it's questions 1 to 6. Problem 1. In this problem, we've got a wave with a frequency of 500 Hz and a phase velocity, a wave velocity of v is equal to 350 meters per second. We can use this to work out the wavelength of the wave. V is equal to f lambda, so our wavelength lambda is equal to v on f, which is 350 over 500, which is equal to 0.70 meters. Okay, that might be useful later on. Part A, it says how far apart are 2.60 degrees out of phase? Well, as a fraction of a wave, there's 360 degrees in the wave, so it's 60 over 360. That's the fraction of the wave. One wavelength is 0.70 meters. So if we times this by the wavelength, we'll get the distance between the 2 points. So solving this on the calculator, a sixth of 0.70 gives us 0.12 meters. Part B, we're asked about the phase difference between two displacements at a certain point at times 10 to the minus 3 apart. Well, let's work out the period of the wave. The period is equal to 1 over 500, so that's equal to 2 times 10 to the minus 3 seconds. We're asked, here's our wave travelling along, if we select a displacement and then wait for 1 times 10 to the minus 3 seconds, what is the phase difference? So this wave is travelling along over this point, and you can see that since this is half a period, we will be 180 degrees or pi radians out of phase. Problem 2. In this problem, we've got a string, and the string vibrates, and then there's reflections, and we end up with a wave that obeys the equation y is equal to 0.5 sine pi x on 3 cos for 40 pi t. Now this is made up of the superposition of two waves. So what we need to do to start this question is to work out what are the two waves making up this superposition. So to do that we can make use of the formula sine A plus sine B is equal to 2 sine A plus B on 2 cos A minus B on 2. So A plus B on 2 is equal to pi x on 3, and a minus b on 2 is equal to 40 pi t. So a simple solution to this is a is equal to pi x on 3 plus 40 pi t, and b is equal to pi x on 3 minus 40 pi t. Then when we add these together, this term will cancel out and we'll end up with this, and when we subtract them, this one from this one, this term and this term will cancel out and we'll end up with that. Okay, so notice there's a 2 here and there's a 0.5 there, so 2 times the amplitude is 0.5, so we have the wave 0.25 sine pi x on 3 plus 40 pi t, that's one wave, and then the other wave is 0.25 sine pi x on 3 minus 40 pi t. Okay, now part A asks what is the amplitude and velocity of the component waves whose superposition can give rise to this vibration. Okay, so we've got the component waves, the amplitude is equal to 0.25. Now we're told that this y is in centimeters. T is in seconds. X is in centimeters as well. So this is 0.25 centimeters is the amplitude. And then we're asked for the velocity. So we can work out the frequency and the wavelength. The wavelength is K is equal to 2 pi on lambda is what comes before the x in this equation. So this is equal to pi on 3. So those pi's will cancel out, telling us that lambda is equal to 2 times 3, so 6.0 centimeters. And in front of the t we have omega. So omega is 2 pi, f is equal to 40 pi. And so our frequency is equal to 20. And then v is equal to f lambda, so that's 6.0 times 20. This is in hertz or inverse seconds. And so this is equal to 120 centimeters per second. Or 1.2 meters per second if you want. Part B says, what is the distance between nodes? Well, as you know, for a wave, nodes occur every half wavelength. And we've got lambda is 6 centimeters, so it's 3.0 centimeters between nodes. Another way to do this part would be to choose any time, say t equals 0 to make it easy, and then work out the two places where, and then work out for y equals 0, 1x, and then the next x, and take the difference between them. But since we'd already worked out the wavelength, this was much faster. Part C says, what is the velocity of a particle of string at the position x equals 1.5 when t is equal to 9/8? Okay, let's just get some more space for this. So for this part, we've got that x is equal to 1.5 centimeters and t is equal to 9/8 seconds. And we know that y, the displacement of the piece of string, is 0.5 times sine pi x on 3 times cos of 40 pi t. Now, in order to get the speed of the piece of string, we're going to have to differentiate this. So we've got dy dt. So 0.5. Now, sine pi x on 3 is not a function of t, so it's just a constant when we differentiate with respect to time. So we've got times sine pi x on 3. And then we need to differentiate this part with respect to time. So when we differentiate this part with respect to time, we get the 40 pi out the front. And then when we differentiate the cos, we get negative sine of 40 pi t. So this is equal to minus 20 pi sine pi x on 3 times sine of 40 pi t. And now what we're going to need to do is work it out at 1.5. X is 1.5 and t is 9/8. So this is equal to minus 20 pi sine. Now this is pi on 3. X is 1.5, which is 3 on 2. So this is pi on 2. So sine of pi on 2, this is 1, times sine of 40 pi times 9/8. And so this, the 8 will cancel out with, this is 8 times 5, so we'll end up with 5 times 9, or 45 pi. And sine of 45 pi is 0. So when we multiply anything by 0, we get 0. So the answer to this one is just 0. Problem 3. In this problem, we've got a piece of wire constructed of two metals. It's hung over a pulley with a 10 kilogram mass hung off the end. This first metal is aluminium. It's got a length L1, which is 60.0 centimeters, and aluminium, we're told, has a density of 2.60 grams per centimeter cubed. And the second one is steel. It's got a length, we're told, of 86.6 centimeters and a density of 7.80. grams per centimetre cubed. The cross-sectional area of the wire, we're told, is 1.00 times 10 to the minus 2 centimetres squared, which we can write as 1.00 times 10 to the minus 6 metres squared. There's a frequency generator attached here, which can send waves with different frequencies down this wire. In part A, we're asked to find the lowest frequency for which we observe standing waves in this case. Now, to have a standing wave, it implies that this length here has to be made up of an integer divided by 2 number of wavelengths. So we've got n1 on 2 times lambda 1 is equal to L1. And we have standing waves here as well, so we have L2 is equal to N2 on 2 times lambda 2, where N1 and N2 are integers. We now need to try and find what these integers are. So first of all, we have V is equal to F lambda, which tells us that lambda is equal to V over F. So let's make that substitution. We've got L1 is equal to N1 on 2 times V1 on F, and L2 is equal to N2 on 2 V2 on F. This frequency is the same. The two types of metal both vibrate at the same frequency, the frequency of the frequency generator. For V1 and V2, we can work out what they're going to be using V is equal to the square root of the tension over the mass per unit length. So this is equal to the square root of the tension over the density, which we've been given, times the cross-sectional area. So let's substitute that in now. We've got N1 on 2 times 1 on F times the square root of T over rho 1A. And for this one, we've got N2 on 2 times 1 on F times the square root of T over rho 2A. Now, what we're trying to do is find N1 and N2. We know these frequencies are the same for both of them, so let's rearrange it for frequency. Frequency is equal to N1 on 2 times 1 on L1 root T on rho 1A. And this is the same frequency, N2 on 2, 1 on L2, T on rho 2A. Now we're trying to find N1 and N2, so let's do N1 on N2 is equal to, now we've got lots of common factors, the 2's, the T's, the A's, so we can ignore all these common factors, and we end up with L1 on L2 is it times the square root of rho 1 on rho 2. Now, these have the same units, these have the same units, so we don't have to worry about converting our units into the normal form. So we've got 60 on 86.6 times the square root of 2.60 over 7.80. Solving that on the calculator, we get 0.40. So we want N1 and N2 to be integers. The smallest integers that we can have satisfying this are N1 is equal to 2 and N2 is equal to 5. Okay, but the question hasn't asked us to find N1 and N2. That was what we had to do to answer it. It's asked us to find the frequency. So now I've got the equation for the frequency right here, so we can substitute in. The frequency is equal to N1, which we've just worked out is 2 on 2, times 1 over L1, which is 60 centimeters, so that's 0.600, times the square root of the tension, which is generated by this 10 kilogram mass, so that's 10 times 9.8, over the density, so it's 2.60. Now that's grams per centimeter cubed, so we need it in kilograms per meter cubed. So times 10 to the minus 3 to get it into kilograms, and 10 to the 6 to get it into meters cubed. And then the surface area, which we've got, is 1.00 times 10 to the minus 6. Solving that on the calculator, we end up with 324 hertz. So that's our frequency. Now part B says what's the total number of nodes observed at this frequency. Okay, so the best way to work out this is to actually draw the diagram. So N1 is 2, so we've got 2 half wavelengths in here, and we've got 5 half wavelengths here. So that's 2, 3, there's 5. 1, 2, 3, 4, 5. And now it asks us to count the number of nodes, but to exclude the 2 at the two ends. So I've got 1, 2, 3, 4, 5, 6. So the answer to B is 6. Problem 4. We have a harmonic wave function. Y is equal to 2.0 meters times sine 2 pi on lambda x minus vt. This is meters. Where y is the displacement in the y direction, so the particles are moving up and down. We're told that the frequency is equal to 2.0 hertz, and that x is equal to 0, and that t is equal to 4.0 seconds, and we're asked to find y. So all we need to do is substitute in. Now we know that v is equal to f lambda, which tells us that v over lambda is equal to f, which is equal to 2.0 hertz. So we'll need to use this fact when we substitute in. So we have y is equal to 2.0 sine. Now 2 pi lambda times x, where x is 0, that's 0, minus 2 pi v over lambda t. V over lambda is 2 and t is 4. So this is equal to 2.0 sine of minus 2 times 2, that's 4 times 4, minus 16 pi. Sine of minus 16 pi is 0. So this is equal to 0. And so 0 is the displacement in the y direction. Problem 5, which is for 1131 only. So in this one, we are given a function y xt is equal to a sine 2 pi on lambda times x minus vt. And we're told that k is equal to 2 pi on lambda, and we're asked to write this in two alternative forms. So the first alternative form, all we need to do is make a substitution. So we have sub in k, should always write down what we're doing. So we have y xt is equal to a sine. Now this is k, so this is kx minus vt. We've done part 1. Part 2, we need to extend this a little bit. We've got a sine kx, and now we've got minus kvt. So this is equal to a sine kx minus k, which is 2 pi over lambda vt. And then we know that v is equal to f lambda. So this tells us that v over lambda is equal to f. So we've got this whole thing here is equal to a sine kx minus 2 pi ft. And then 2 pi f is just omega. So this is a sine kx minus omega t. And that's y xt. So there we go, we've shown that. Okay, now problem 5 for 1121 or 6 for 1131. We're shown a photo and we're told that we have an acoustic microscope with a frequency of 3 gigahertz, which is 3 times 10 to the 9 hertz. And that the speed of this ultrasonic wave is given by 1.5 kilometers per second, which is 1,500 meters per second. And we're then asked to calculate the wavelength. Well, v is equal to f lambda, telling us that lambda is equal to v on f, which is 1,500 over 3 times 10 to the 9, which is equal to 5 times 10 to the minus 7, which we can write as 500 nanometers. So this is 500 times 10 to the minus 9 meters, 500 nanometers. We're then asked to compare this wavelength to the wavelength of green light, which is what's apparently used to take this photo. Well, light is in the wavelengths around about 400 nanometers. That's blue to about 750 nanometers for red. So green is around just over the 500 nanometer mark. So these waves have similar wavelength, which is actually why they're showing a similar detail in that photo. The finest detail you can generally see is around about equal to the wavelength of the light that you're using to illuminate the object. So as the light we're using to illuminate this object has the same wavelength in both cases, we'll see similar features.